Hello and welcome to our first video in the series of partial fraction decompositions. In this first video, we are going to discuss a theorem related to partial fraction decomposition, and we are going to discuss a general process for determining these decompositions. And our second video in our series will be specific to demonstrating examples with distinct linear factors. So initially, our procedure for decomposition starts off with these steps. Before you begin, make sure the numerator function and denominator function are relatively prime. What this means is that they do not share any common factors. If they do share common factors, you may end up with larger systems than what are necessary and have zeros for those coefficients involved in the decomposition. So if you make sure that these numerator and denominator functions are relatively prime, you do not have to have this excess involved. So after you reduce your fractions down and that the numerator and denominator do not share any common factors, then we can begin our decomposition process. And the first step in the decomposition process, after you reduce the fractions down, is to make sure that you have a proper fraction. The degree of the numerator is greater than or equal to the degree of the denominator. You have to use some kind of division process to obtain a remainder. And you apply the decomposition to the remainder rational function rather than the original. So if the degree of the denominator is greater than the degree of the numerator, then you may continue in the process. So the very first thing you have to do is you have to check the degree of the numerator, the degree of the denominator, and you have to have what's called a proper fraction. When you have rational functions, then you have to make sure that the degree of the numerator is strictly less than the degree of the denominator. Otherwise, you will have to do a division process of some kind and reduce the rational function down to a proper fraction so that we may proceed. Our second step is to factor the denominator function into a product of factors. Since our next video in the series is specific to linear factors, we will go ahead and say factor the denominator function into a product of linear factors. Because f and g are polynomials and the degree of g is less than the degree of f, this means that g is the numerator polynomial, f is the denominator polynomial. We can always rewrite f of x as a product of these factors. This is because of the complete factorization theorem from polynomial theory. So once we get our factorization from step 2, each of our factors from our denominator polynomial is going to correspond to an individual denominator for my decomposition. So we're going to set up a format or a template for the decomposition as having some number. We call it A1 here. We don't know that number. We're going to find out what that number is. And we're going to divide that by one of our factors from the denominator that we found from step 2. And then we're going to add another constant. We don't know this constant. We call it A2 here. And we're going to divide that by another factor in our factorization of the denominator. And we continue this until we exhaust all of the factors. After we get to step 3, we get our template down. We are going to recombine these fractions and match the coefficients of the powers of the variable x. So we're going to take this A1 number and multiply by all these other factors for the denominators of all the other fractions. And then we're going to add A2, and we're going to multiply by this factor, skip over the denominator for A2, and then multiply by all the remaining denominators that form the factorization of f. And we're going to do that for each one of these. And that's going to give us our equation that we're trying to match the coefficients with. And then we're going to set up a system of equations and we're going to solve that system. Now, when it comes to distinct linear factors, there are several techniques that are usually employed, such as cover-up methods, substitution methods, and even some methods from calculus that help to determine what these coefficients A1, A2, all the way up to AN are. But we are going to use systems of equations here in these demonstrations because we don't have to worry about learning new techniques. The system of equations technique is going to cover all of our cases. So in this first video, when we introduce our process, we are going to just focus on solving a system of equations. When we set up the rest of our videos for the individual cases, then we will still have a system of equations that we're going to solve. So this step 5 here, set up a system of equations and solve it. This is going to be the uniform methodology that we're going to use to determine the coefficient values, A1, A2, all the way up to AN, so that we have just one process for this decomposition. So the reason why matching coefficients work, this comes from linear algebra a little bit, is that two polynomials are equal to each other if and only if the coefficients of each of the powers of x are equal to each other. This is what I mean by matching coefficients. Now, to see this in a little bit more detail, let's look at an example. Let's have 2x plus 1 divided by 2x squared minus x minus 6. We're going to simplify this down into partial fractions. So our first step is to check to see if this rational expression is in lowest terms. We go ahead and factor the denominator, and we see that there are no common factors in the numerator with the denominator, so we know that it's in lowest terms. The denominator has no repeated factors, so we may go ahead and write the right-hand side as a over 2x plus 3 and b over x minus 2. This decomposition comes from the fact that the degree of the numerator is 1, the degree of the denominator is 2, so there are no long division processes needed. This is a proper fraction. And now we're going to determine the values of capital A and capital B. And when we do this, we go ahead and recombine the fractions as we see here. Go ahead and take the A value multiplied by the denominator of B, add the B value times the denominator underneath the A guy, and then we just start combining like terms. So our system of equations becomes A plus 2B equals 2. These are the coefficients of x. Then we have negative 2a plus 3b equals 1. These are the constant terms, okay? And this is the system of equations that we are required to solve. Now, there are many, many techniques for solving systems of equations. You have substitution, you have elimination, you have matrix method, you have Cramer's rule. What's used in this demonstration here for A and B at top are Cramer's rule for determining the solution to systems. So we know that we can rewrite 2x plus 1 divided by 2x plus 3 times x minus 2 is equal to 4/7 divided by 2x plus 3 plus 5/7 divided by x minus 2. And this is our decomposition for our original fraction. So what makes this possible? Why is this able to be done? And one reason why this is able to be done is because of the theorem that you have here. This theorem in this box is the partial fraction decompositions theorem. And what it says is as follows. Let P of x divided by Q of x be a rational function where P of x and Q of x are polynomials such that the degree of P of x is less than the degree of Q of x. Okay, so this forms our first step is checking the degrees of this rational function. Check the degree of the numerator, check the degree of the denominator. And make sure that you satisfy the condition of being a proper fraction. The degree of the numerator is less than the degree of the denominator. If this is the case, then there will exist algebraic fractions, F1, F2, all the way up to FR, if you will, so that I can rewrite this rational function as a sum of these algebraic fractions. Now, these algebraic fractions have the form that you either have a constant divided by some linear factor raised to a power, or you have some linear expression that I'm highlighting here in blue, divided by some irreducible quadratic factor. So what's going on here is that if you have a rational function where you have real coefficient polynomials, then this statement down here that says that each quadratic expression has negative discriminant, all that means in plain language is that the roots to these quadratics are complex numbers. They are not real numbers, and therefore they are what we call irreducible quadratics. Once you have these capabilities, once you have a proper rational function, you have the ability to write it out as a sum of fractions in one of these forms, and the quadratics cannot be broken down any further over the real numbers. You are guaranteed the existence of a decomposition. And this is what enables us to do a partial fraction decomposition. And what this does is that it enables us to write a complicated rational function as a sum of simpler rational functions. And this is the reason why we do it. So this theorem here, along with our steps for doing the partial fraction decomposition, we'll go ahead and review those really quick. Our first step is to make sure that you are in a reduced form. Then we check the degrees of the numerator and denominator, make sure that the degree of the denominator is strictly larger than the degree of the numerator. Then we factor the denominator into a product of linear factors. This is for the discrete linear case. Then we go ahead and rewrite this rational function as a sum of a constant divided by a linear factor for distinct linear factors. Then we're going to add these things up. We're going to add up all these fractions, just like you normally would, find common denominator, get the numerators to match up. And that will enable us to match the coefficients on the powers of x. And after that, we're going to set up a system of equations and we're going to solve it. And that's going to give us our coefficients, a1, a2, all the way up to an. So this is the process that we're going to follow when we talk about distinct linear cases in the next video. Repeated linear factors in the video after that, and then we'll talk about how to do quadratic factors, irreducible quadratic factors, so that we can see all of the cases for partial fraction decomposition. So see you in the next video, and thank you for your time and attention.